Welcome back. So our first slide here poses a question to us, asking what if you have more solute than is soluble? So for example, you have some water in a beaker and you dump a bunch of table salt into it. Now, I'm sure at some point in your life you have either been to the ocean or you have yourself put salt into water, maybe for a salt mouthwash or something like that. You are most likely well aware that you can dissolve a whole bunch of salt in water, but there is a limit to how much you can dissolve in water. If you put too much into the water, you'll just end up with salt sitting at the bottom of the cup or beaker or whatever it is that you're using. And again, that is because of the solubility of the material. There is a limit to how much will dissolve. Now, when you reach that point, when you've put more into the solution than can actually be dissolved in the solution, you put too much solid, and so you end up with solid sitting at the bottom of the container. What's happened there is not that you've reached the solubility and so therefore nothing more dissolves. It's not what's happening at all, actually. It is still continuously dissolving for the rest of time that it's there. If you seal it up and keep it in there, it will still, for the rest of the time that it has in that container, it will continuously be dissolving. But what's also happening is that some of the molecules that dissolve into the solution recrystallize. Some of them drop out of the solution, essentially. And the solubility of the material is when those two rates, the amount of stuff that's dissolving and the amount of stuff that is dropping out and recrystallizing, are exactly equal to each other. And so that's going to be slightly different for every material, and we'll talk a bunch more about this in chapter 16, I believe, about solubility and the kinetics and the equilibria that's at play here. But for now, we're just talking about solutions in general, and this is what we would call a saturated solution, where you have put as much stuff into the solution as can possibly be held, to the point where there's actually some solids sitting at the bottom. It is completely saturated. Just one quick aside here, there is actually a way of getting around certain kinds of saturated solutions. You can create what we call a super saturated solution. The easiest way to do this is to take a solution that is saturated, so you have as much stuff in the solution as possible, and you even have some solid sitting down at the bottom, and then you heat it up. As we'll talk about in just a second, when you heat most solutions up, that increases the solubility of the material, and so you will end up dissolving that extra solid that was sitting at the bottom. And then for certain solutions, in certain circumstances, it doesn't work every time, but for certain solutions, if you cool it down very slowly, you can, in a sense, trick the solution. You can trick the solution into having more solute dissolved than should be allowed. And again, this is called a super saturated solution. These are very unstable solutions, not unstable in terms of they're going to explode or anything, but nearly any kind of either hard physical jarring of the material or introduction of some kind of a template into the solution will cause that extra stuff to drop out of solution and form crystals, which is what you can see here. So this is a supersaturated solution, and they drop in a little what's called a seed crystal. And that seed crystal simply provides a template for the molecules that are supersaturated in the solution to grow off of. And that's why you can see those tendrils coming out. That's not the glass being broken. That's actually tiny little crystals that formed off of the faces of that seed crystal. So it's a pretty cool little thing that can happen with these supersaturated solutions. I would actually encourage you to go to YouTube and look up some videos of supersaturated solutions. They can be really cool. There's one in particular that I like to watch sometimes where there's a supersaturated solution and a guy covers his hand in seed crystals and then sticks his hand down into the beaker and he pulls it out with a crystal glove on his hand. I would not suggest you doing that, but in the video it looked very cool. Okay. One last thing here for this video. When we're talking about solutions, there's a few subcategories of solutions that we will come across. There are what we call electrolyte solutions. So this is a solution where the solute is made up of an ionic compound that breaks apart in solution. So electrolytes, you've heard of these, I'm sure. People talk about needing, get your electrolytes, like if you work out or something like that, you need to replenish your electrolytes. They're literally referring to ions in your blood, essentially, in your body that need to be replaced. These are ionic compounds that are dissolved in your blood. And so these electrolyte solutions, like I said, they are made up of ions that are dissolved, and because they're made up of ions that have broken apart into their positive and negative constituents, they conduct electricity. So table salt is an example of this, where if you dissolve table salt in water, the water will conduct electricity, whereas water with sugar does not conduct electricity. It's actually a fairly common misconception among people that water conducts electricity. Pure water does not. Pure water is actually a really bad conductor of electricity. The thing is, nearly all water you come across has all kinds of stuff dissolved in it. Even your tap water, even though it doesn't, it's just, we think of it as being pure water, there is actually a decent amount of stuff in the water, which is not dangerous. I'm not saying that there's stuff in the water, no, nothing like that. It's just stuff that's perfectly fine and safe to be there. But there are things dissolved in the water. And we actually need stuff to be dissolved in the water. It's actually not terribly healthy for us to drink truly pure water because you, as we were just talking about a second ago, you will deplete your body of electrolytes. You actually need some electrolytes in the water that you drink. So anyway, pure water is actually not electrically conductive. Pure water is actually insulating. It's only once you put an electrolyte into it that it becomes conductive. And tap water, even though it does have some stuff in it, it's not enough for it to conduct very well. It conducts a little bit. Just a little bit. Not very much. You'll also have non-electrolyte solutions. So this would be like the table salt from the previous slide there. These are solutions where the solute exists as a molecule in the solution. It does not break apart, so it is still picked up by the water molecules and carried around, but the water molecules are not ripping the molecule apart like it did with the ionic compounds. With the ionic compound back here, the water really likes the sodium and the water really likes the chlorine. Different ends of the water molecule like one or the other, but with the sugar here, or methanol, the water still likes those molecules, but it can't rip them apart. It can't separate them. So these do not conduct electricity. And then we will also have what we call weak electrolyte solutions. So we had strongly electrolytic solutions, where you have molecules that completely dissociate. This is going to be most of the ionic compounds that we are going to look at. And then there's some other solutions where the molecules kinda sorta dissociate, where some of the molecules will break apart into different ions, but most of them don't. So acetic acid is an example of this. Acetic acid, about 1 in every 10,000 or so of the acetic acid molecules will actually break apart into acetate and hydronium ion. And we will talk a whole lot about this in chapter 13, I believe it is. We'll talk a lot about weak electrolytes. We're just getting introduced to them here. So strong electrolytes, we have compounds that completely dissociate in water. They strongly conduct electricity. Weak electrolytes, similar, but they don't break apart completely. Most of the molecules stay whole. They stay as a whole molecule, and only a few of them break apart. And so they weakly conduct electricity. So you can see that here with the light bulbs, where the strong electrolyte, the light bulb is very bright because there's plenty of conductivity. The weak electrolyte, you have a little bit of conductivity, and so it's dimly lighting the bulb. And then the non-electrolyte is just not even there. There's really no conductivity at all. Alright, we'll call it there for this video, and the next one will pick up with temperature effects on solubility. So I'll see you there.